So those are the special triangles. And what I want you to kind of see about special triangles, right, is this is certainly the way that I wrote it the first time, where the side lengths were 1, 1, and √2. Thank you. For the 45, 45, 90 triangle. But you can scale those triangles by any factor you want. So you can totally multiply this by 3 and have it be 3, 3, and 3 √2. Or specifically here, I've divided everything by the square root of 2. So this side is 1. This side is 1 over √2, which rationalizes as √2 over 2. And so is this side over here. And the same thing is true about really any triangle. You can scale by whatever factor you want, and the angles remain the same. These are called similar triangles. Not that we really talk about them in this class, but similar triangles are triangles that have the same proportions and the same angles, are just different in size. Here's our other special triangle, the 30, 60, 90 triangle. And usually we write the sides as being 1 and √3 and 2, but I've decided to scale them by dividing each of them by 2. So that side's 1, that side's 1/2, and that side's √3 over 2. The point being that I kind of want to look at these triangles so that they have a hypotenuse of 1. Because when we talk about the unit circle, the radius of the unit circle, which ends up being the hypotenuse of your right triangle, has a length of 1. So you don't need to copy this down. You're certainly welcome to if you want to. I will definitely post it later, but I'm going to reference back to this as we talk about the unit circle. Let's see if I have enough room to keep it on the screen. I might. We might be able to fit all the things on at once. Let's see if we can do that. That might work. So let's talk about, I don't know why this says tree graphs on it. This tree graphs is later. Apologies. Tree in these, but really this is more unit circle. So here is our circle with a radius of 1. It's got some important points on the axes, 1, 0, 0, 1, etc. -1, 0, 0, -1. But here's what I want to point out. If you start from the positive x-axis, draw some segment there. That angle theta, well, if I drop a perpendicular from this point to the x-axis, I'm going to call this distance along the x-axis x, that distance along the y, along the height of this triangle y, and I've gone over x and up y, so I'm going to call that point x comma y. And what I want to see really is that if I look at sine of theta, well, the hypotenuse of this triangle is the radius of the circle, which is 1. So if I want to find sine of theta is going to be the opposite of the hypotenuse, which is just y, or y over 1. And cosine of theta is going to be the adjacent of the hypotenuse, which is x over 1, which is just x. The tangent of theta is going to be the opposite over the adjacent, which is y over x. And then it seems, yeah, that's a good question. How do I know to make the triangles? Memory is kind of the truth. I do remember that the 45, 45, 90 triangle, if you're trying to reconstitute them, the one way you can think about how to make these triangles, here for a second, is that the 45, 45, 90 triangle is an isosceles triangle. So this side and this side should be the same, and you can use the Pythagorean theorem to find the third side. For the 30, 60, 90 triangle, you can kind of remember if you want that it's half of an equilateral triangle. I mean, in truth, I would encourage you to memorize the triangles. But if you have trouble memorizing them, you can reconstitute them or re-derive them by remembering, oh yeah, this here is an isosceles triangle, the side lengths are the same. This here is half of a equilateral triangle. So we know the angles are 60, 60, and 60, and then this angle gets cut in half and becomes 30. And you can find the sides again using the Pythagorean theorem. So I want to not miss an opportunity here to mention that if you look at tangent of theta and see that it's y over x, well, what's y equal to? Sine of theta. And x is equal to cosine of theta. So it should be not too hard to see that, oh yeah, you can think of tangent of theta as sine of theta divided by cosine of theta. And I really don't, I don't want to really, but I will point out that if I was going to find cosecant of theta, I would think of it as 1 over sine of theta. Now you could also note that cosecant of theta, being the reciprocal of sine, is going to be 1 over y. And secant of theta, being the reciprocal of cosine, is going to be 1 over x. And cotangent of theta, being the reciprocal of tangent, is x over y. And if you like, you could also say that cotangent is which trig function divided by which trig function.
Just to clarify, so it would be sine over cosine because like the hypotenuse denominator would cancel out, right?
Right, exactly. Yeah, so you could totally think, right, tangent of theta is y over x and sine is theta and cosine, and sorry, y is sine theta and x is cosine theta. But you could also, there's another way of seeing this where, like, in fact, let's go ahead and do that for a second. Just to kind of clarify what Tyler said there, if you were back in like a regular old triangle situation, a right triangle, and you were like, okay, well, that's my opposite, so that's my opposite, that's my adjacent, that's my hypotenuse. Tangent of theta is opposite over adjacent. And sine of theta over cosine of theta, well, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. And oh yeah, when you have division of fractions like that, you flip and multiply. So we get opposite over hypotenuse times hypotenuse over adjacent. And the hypotenuse is canceling. You exactly get opposite over adjacent, which is tangent. I think that's what you were saying. Like, yeah, exactly. That's exactly what's happening there. All right. So I'll try and keep this on the screen here. That's kind of the big deal about the unit circle, is that on the unit circle, literally the point on the circle is cosine of the angle for the x coordinate and sine of the angle for the y coordinate. So for example, although we're going to kind of come back in a minute, you could look at this coordinate here, which is associated with an angle of 0 degrees, and say, oh, cosine of 0 degrees is 1. Sine of 0 degrees is 0. And we mostly, at least I think, we mostly use the unit circle to evaluate trig functions of angles that don't make nice triangles. Or in other words, angles that end up living on one of the axes, which are called quadrantal angles, which I just love to say. Quadrantal is a fun word, but any angle that terminates on the x or y axis is a quadrantal angle, and you can't really make a triangle that has that angle. Eric, you have a question?
Yeah, did you put 1 as the hypotenuse because like the coordinates are 1 or something?
I put 1 as the hypotenuse because the circle is the what circle? The unit circle. And the unit circle has a radius of 1. So that's why we get to pick 1, because we are deciding, oh, this circle is a unit circle, has a radius of 1.
So if it was like a different number than that, would be the number.
Right. So if the radius wasn't 1, then sine would be like y over whatever the radius was, and cosine would be x over whatever the radius was. So this nice fact that the coordinate on the circle is equal to cosine theta, comma sine theta is only true if the circle has a radius of 1. Other questions about this? All right, so we're going to fill in the unit circle, which again, I don't know if it's the best use of your time necessarily, but I know it's how it's how some people like to do it. So let's talk about this first angle here. Actually, the first angle is an angle of 0. So right here, we have theta is 0, or if you go all the way around, 2 pi. This angle here, theta is going to be pi over 6. And the coordinate that goes, and I'm going to zoom a little bit so you guys can see that better. And the coordinate that goes with pi over 6, well, cosine of pi over 6 we know is 1/2. And sine of pi over 6 is the square root of 3 over 2. I got that backwards. Wow. Sorry. I just feel like my brain is like, ooh. That's totally not right. Those are totally interchanged. Now, let's look at why that's wrong. If you make a mistake, it's good to think about why it's a mistake. If you look at this point, which value should be bigger? The x value or the y value? Have I gone more over or more up? I've gone more over. So it seems like the x coordinate should be the bigger coordinate. And it should be. It's not the way I've written it, right? 1/2 is definitely smaller than the square root of 3 over 2. That should actually be the square root of 3 over 2, 1/2. Now, what I should have done is look at my triangle and said, okay, looking at the triangle that goes with that angle of pi over 6, which is 30 degrees, cosine is the adjacent over the hypotenuse, which is the square root of 3 over 2 over 1. And sine is the opposite of the hypotenuse, which is 1/2. Let's look at our next angle. Our next special angle is pi over 4 radians, which goes with this triangle over here. And if we look at cosine of 45 degrees, which is the adjacent over the hypotenuse, that's going to be root 2 over 2. The nice thing about pi over 4 radians or 45 degrees is that sine and cosine have the same value. Which kind of makes sense if you think about it, because if this angle is 45 degrees or pi over 4 radians, that's on the line y equals x. If you're making a 45-degree angle, you're on the line y equals x. And so the x and the y value should be the same. And the cosine value is the x coordinate, sine value is the y coordinate. So those should have the same value. And then for theta equal to pi over 3, well, looking at the 60-degree angle here, cosine of theta is 1/2 over 1. And sine of theta is opposite over hypotenuse, which is root 3 over 2 over 1. And now we have filled in the first quadrant of the unit circle. I suppose I could also write this angle here is pi over 2. So now, here's the nice thing about the unit circle. You only have to memorize one quadrant of it, if that's the way you want to do it. Because there's a lot of symmetry. So what I want you all to see here is that this coordinate, if I look over here, the x and the y value should be the same, except that which one is now negative? The x, right? I flipped this over. My x value is negative root 3 over 2. My y value is still positive 1/2. And the angle is 5 pi over 6. The angle in the second quadrant that has pi over 6 as the reference angle. So this is why we see that trig functions of angles with the same reference angles essentially have the same values. Sine of pi over 6 is 1/2. Sine of 5 pi over 6 is also 1/2. Cosine of pi over 6 is root 3 over 2. Cosine of 5 pi over 6, well, I know the reference angle is pi over 6. I know it's in quadrant 2. So cosine of 5 pi over 6 should be negative root 3 over 2. So I don't think you need to memorize the rest of the unit circle, but I want to show you the symmetry of it because it kind of reinforces the idea of, oh yeah, you can just use whatever values in the first quadrant and then determine the positive or negativeness based on what quadrant your angle actually lives in. So here, this angle is 3 pi over 4. Angle is, whoops, I want to use black there, sorry. I said pi over 3, I wrote pi over 6. I think my brain doesn't want to work so much anymore. Sorry about that. That should definitely be pi over 3. I think I said pi over 3.
You did. I wrote that.
Okay, well, good. I'm glad at least I said the right thing. This angle here is going to be 2 pi over 3. And for this angle, well, it's going to have the same values as the reference angle for it, but the cosine value, the x coordinate, is going to be negative. And same deal here. This angle is going to have the same values as this angle, just the x coordinate is going to be negative. If we keep going the same way, well, in the third quadrant, this angle is 7 pi over 6. This angle is 5 pi over 4. This angle is 4 pi over 3. And the associated values are, well, for 7 pi over 6, now everything's going to be negative in this quadrant because x and y are negative. That's going to be negative root 3 over 2, comma, negative 1/2. And that's going to be negative root 2 over 2, comma, negative root 2 over 2. And that's going to be negative 1/2, comma, negative root 3 over 2. And lastly, in the fourth quadrant, this angle now is 5 pi over 3. This angle is 7 pi over 4. This angle is 11 pi over 6. And the values are, now the x coordinate's positive, the y coordinate's still negative. So 1/2, comma, negative root 3 over 2. Oh, sorry. Okay. Sorry, someone asked, do I know it's pi over 6 because of memory? And partially, yeah, but also because of how it's positioned from the x-axis here. It's going to be positive root 2 over 2, comma, negative root 2 over 2. This last one's going to be positive root 3 over 2, comma, negative 1/2. So a few things to observe here. I've tried to color code things so that all of the angles with the same reference angle are the same color. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 all have pi over 6 as a reference angle. And they all have a cosine value that's either positive or negative root 3 over 2, and a sine value that's positive or negative 1/2. And then for angles that are pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, which all have a reference angle of pi over 4, they all have a sine value and a cosine value that's either positive or negative root 2 over 2. And then for all the angles with pi over 3 as reference angle, which are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, all the cosine values are positive or negative 1/2, and all the sine values are positive or negative root 3 over 2. So angles with the same reference angle have essentially the same values for their trig functions. You just have to adjust whether it's positive or negative. And the way we do that is by remembering that in the first quadrant, all things are positive. In the second quadrant, sine is positive. In the third quadrant, tangent is positive. And in the fourth quadrant, cosine is positive. Oh, sorry. Question first.
Is there a reason why you like kind of skip some angles?
Say that one more time.
Is there a reason why you kind of skip?
Oh, you mean like the ones that are on the axes?
Well, for the last quadrant.
Maybe I wrote the pi 3 not even, so I kind of so this line here is going with that angle there.
Right. Oh, okay.
I didn't skip any. I just wrote it in not the same.
Oh, so does it matter which one you write it?
Right, like I meant, yeah, I should have written it above here. I can make that a little more obvious. No problem. And then to fill in the quadrantal angles, this angle here is pi. This angle down here is 3 pi over 2. Something worth noting. If you're wondering what quadrant an angle lives in, the way you can kind of think about it is, well, let me show you an example. Let's say we were looking at 7 pi over 6. And I didn't know that it was just a little bit bigger than pi in the first quadrant. The way you can figure out which quadrant it lives in is, well, 1 pi over 6 is in the first quadrant for sure. 2 pi over 6 reduces, 3 pi over 6 reduces, 4 pi over 6 reduces, 5 pi over 6 is the next one that doesn't reduce. it's in quadrant 2. 6 pi over 6 definitely reduces. 7 pi over 6 doesn't reduce. It's the next one that's in the quadrant. It's in quadrant 3. 8 pi over 6 reduces. 9 pi over 6 reduces. 10 pi over 6 reduces. 11 pi over 6 doesn't reduce. It's the angle in quadrant 4 with the reference angle of pi over 6. And that pattern holds for all of these angles. Pi over 4 is in the first quadrant. 2 pi over 4 reduces. 3 pi over 4 is in the second quadrant. 4 pi over 4 reduces. 5 pi over 4 is in the third quadrant. 6 pi over 4 reduces. 7 pi over 4 is in the fourth quadrant. 8 pi over 4 reduces. It works for the pi over 3s as well. 1 pi over 3 is in quadrant 1. 2 pi over 3 is in quadrant 2. 3 pi over 3 reduces to pi. 4 pi over 3 is in quadrant 3. 5 pi over 3 is in quadrant 4. It's kind of a neat pattern. It's one way you can do it. It's kind of a long way of doing it, right? It's not like the best, fastest way of doing it, but it is something that works if you're trying to figure out what quadrants it's in. Now, it's probably easier to change it to degrees than be like, oh, well, obviously if it's in degrees, I can tell what quadrant it's in because it's just easier to see. But it is good to get, kind of practice with knowing what quadrant a radian angle is in. Other questions? I see looks on faces that feel like there might be a question on your face, really, and not to call you out, but like, I feel like you have a question, you're just not maybe sure what it is.
Yeah, I don't really know what to ask.
Okay.
Like, okay, for example, it's probably loaded, but I didn't really understand it from last class either. I think you just explained it, but I'm just gonna ask it.
Go ahead.
If it said, so like last time, so like find the cosine of like 5 pi over 4. And
Right.
you would draw the little like, oh, it's obviously in the third quadrant.
Sure.
I'm like, how do you know? And I'm like, I'm looking at it, it's positive, but why was it in the third one? Like,
So why is it obvious to me that 5 pi over 4 is in the third quadrant? Well, yeah, no, so really the answer is though practice. Like, I mean, I've done it for a long time, right? So it is, I will admit, obviously, oh yeah, 5 pi over 4 is in the third quadrant. But here's why it's obvious.
Is there like a mathematical? Oh, okay, that sounds dumb. Obviously there is, but I'm saying, is it like a long process?
No,
to find it?
it's not a long process.
Okay.
So one way you could certainly do it is you could change 5 pi over 4 to degrees. If you change 5 pi over 5 pi over 4 to degrees, it's going to be 225 degrees. And this, halfway around is 180 degrees. 3/4 of the way around is 270 degrees. In fact, let's write those in there. This is 270 degrees. This is 180 degrees. This is 0 degrees or 360 degrees. And this is 90 degrees. But if I didn't want to do the process of changing it to degrees, I can say, well, I'm always remembering that halfway around the circle is pi radians. And you're asking about 5 pi over 4 radians. So I know I have a little more than halfway around the circle. In fact, 5 pi over 4 is 1 whole pi, which is it's terrible that 1 whole pi is halfway around. There is, so no, I won't say that. It's too much. There's another way people want to do this, but it takes a little bit. So if 1 whole pi is halfway around, and I'm doing 5 pi over 4, I've gone 1 pi. How much more do I have left to do? Not much. 1/4 of pi, which is 1/4 of halfway around. So I know I'm going halfway around plus another 1/4 of halfway around, which is going to keep me in the third quadrant. Now, I do feel like there was a second part of your question.
I think, okay. I don't want to sound dumb.
That's all right.
I don't want you to think I'm like not paying attention.
I don't think you're not paying attention. I know you're paying attention.
Okay. How did you change it to degrees then?
Sure. So the way we change to degrees, and so this is definitely back in class T, I think.
Okay, that's what I was saying.
Sure.
I was like,
But like, so to change it to degrees though, what you would do is you would take your radian measure and we're going to use the fact that 180 degrees is the same as pi radians. And then we're going to say our conversion factor is 180 divided by pi, which is equal to 1. So what we're doing, just like when you change, my kind of go-to is when you change from like feet to inches, right? If I'm going to change from 4 feet to inches, well, I'm only ever allowed to multiply by what number? If it doesn't change something. 1. 1 is the only number you can multiply by that doesn't change a thing. So I have to multiply by 1 if I don't want to actually change the value. Here's the 1 I'm going to multiply by. 12 inches divided by 1 foot. Right, that's 1. It doesn't look like 1, but it is 1 because 12 inches divided by 1 foot is 1. And then the units we don't want cancel, and we get 4 times 12 inches, which is 48 inches, which is the same as 4 feet, just measured in inches. That's the whole idea here, is we're multiplying by this 1 to change from the units we don't want to the units we do want. If I multiply this by 180 degrees, excuse me, over pi, I'm not going to write radians because that's very standard. The pi's cancel. 5 times 180 is 900 degrees divided by 4. I don't like dividing by 4. I like dividing by 2 twice. 900 divided by 2 is 450. 450 divided by 2 is 225. So that's how I'm converting from the radians to degrees there. Other questions? They're good. I'm sure you're not the only one with that question. Yeah.
I have a question, but kind of what helps me with that, if I look at an angle like 5/4, I always know that if like you look at the denominator, it's like over 4, it's always going to be root 2 over 2, either one. So like that's like kind of the way I do it. And then also for the conceptualization of unit circle, like no matter how much I was trying to conceptualize to get myself to understand, I really just had the end memorize the whole thing, and like it just like, really helps because like sometimes the sense of like conceptualization is confusing.
Right.
So that's kind of like why I'm like just like sitting back in this class right now, just because I have the whole thing memorized.
Sure. So if memorizing the whole unit circle works for you, that's what you should do. It doesn't ever work for me. So what I mean, honestly, like I just like, and clearly, right, like I couldn't even, I wrote the wrong thing there when I wrote it down because like I have never memorized this. I remember when I took trig way back when, like I had a hard time with the unit circle. It was not easy for me to memorize it. I had to think about, okay, I know what's going on in the first quadrant here, and then I'm just gonna be like, I don't actually want to fill the rest of this thing in. I want to be like, I know sine of 7 pi over 4 is negative because it's in quadrant 4, and it's root 2 over 2 because the angle has a reference angle of pi over 4, and I know sine of that angle is positive root 2 over 2. But what I really want to say is, do what works for you. That's kind of the mantra of a lot of this class. If it works for you and it's right, that's okay. Okay.
So we should know the triangles though.
I think so. That's I get well.
Those two, the 45.
Yes, if that works for you, right? So like I definitely think I like knowing these triangles. I personally like knowing these triangles. The reasons I pointed out these triangles is because they're the ones where the x and y values actually are the same as the values that are on the unit circle. So like if we were thinking of this as the origin of the unit circle, and this is the point that's on the unit circle, so like, you know, we're doing like that. There's your circle there. You guys can kind of see that maybe, kind of. Right, at that point there is the point I've gone over root 3 over 2, I've gone up 1/2. And the same kind of deal here. If that's the point on my circle.
Isn't it just, well, see, okay, when you have a normal triangle and you do opposite over a hypotenuse, don't we have to then out the answer?
Say that one more time.
Square root of 2 over 2. When if you do opposite over hypotenuse, no, yeah, it'll be 1 over square root of 2.
Right.
And then you do everything, and that's gonna.
Yeah. Yeah. So the kind of not satisfying answer to this is there's a lot of different ways you can do this. Right? You could memorize unit circle. You could memorize the triangles and then say, I know what I'm going to find the cosine of an angle based on the triangle that has the reference angle and the quadrant that the angle is in. Or there's probably lots of other ways of doing it too that I haven't even thought of. But those are a couple ways of doing it that I think work well. Yeah. Other questions, comments, observations?
For the pi over 4, I always thought about it as there's a 1.
Mm-hmm.
So add 2 each time. The next one will be 5. I mean,
So there is, so I will say, there is a trick people do with their fingers that I've never been good at. I don't even want to pretend like I can show it to you.
table.
No, no, it's not that one. I mean, I can do the 9 one, like from, oh yeah, what's that movie? Stand and Deliver? If you haven't seen Stand and Deliver, you should see Stand. It's a good movie. It's an old movie, but it's a good movie. But what I want to say is that there's something you can do with one hand, with your 5 fingers, where like you can do sine and cosine. It's like, if you look at this, if you look at the pattern here in the first quadrant. So let's look here for a second. So sine of 0 degrees or 0 radians is how much? Is it 1 or is it 0? Everybody.
0.
Thank you. Or I'm going to say it's the square root of 0 over 2 to be super annoying.
But that's more complicated.
I know, but there's a pattern. Wait,
Okay.
what's sine of the next important angle,
1/2.
which is the square root of 1 over 2? What's sine of the next important angle? What's sine of the next important angle? Square root of 3 over 2. What's sine of the next important angle? The square root of 4 over 2, obviously. Right, but there is a pattern there. The sine values go from square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. It is a easy in quotation marks. It's an easy-ish pattern to remember. And cosine does the backwards thing. Cosine of 0 is 1, which is square root of 4 over 2. Cosine of the next angle is square root of 3 over 2. The next angle is square root of 2 over 2. The next angle is square root of 1 over 2. The next angle is square root of 0 over 2, which is 0. That is a pattern people often reference about the angles, the sine and cosine values in the first quadrant. So to sum up a little bit, whatever way you can do it, you should do it. And I'm happy to help you try and figure out what way works best for you. I'm kind of showing you what works best for me because that's the way I've always done it. So let's talk about evaluating some of these trig functions using the unit circle. Of course, we're going to start off with something kind of wonky. Sine of 3 pi. So sorry, I'm trying to like get this here so you can still see the thing. So you don't want to do that. Okay, that's fine. I'll just do it like this. So 3 pi, that's not on the unit circle. That angle is bigger than 1 full revolution. So if your angle is bigger than one full revolution, you just keep going. So sine of 3 pi, we're going to go 1 full revolution around. There's 2 pi, and then a whole nother pi. So sine of 3 pi, the angle terminates right there. With a coordinate on the unit circle, that's what? Well, that point on the unit circle has a coordinate of -1, 0. And we know that the sine value is which? The x or the y? The y. And if you ever forget, remember it's alphabetical. Sine comes alphabetically after cosine, holy smokes. Cosine before sine, x before y. So sine of 3 pi is going to be 0. And just to add in, cosine of 3 pi would definitely be -1. And I will mention that the unit circle is specifically useful for finding sine and cosine and other trig functions of quadrantal angles, the angles that end up stopping at the x-axis or the y-axis. If I want to find cosine of 5 pi, well, in fact, that's actually the same. Cosine of 5 pi is just 1 whole more revolution. So cosine of 5 pi is also -1. Here's 5 pi. Yeah, so 2 pi is 1 full revolution.
Oh, okay.
4 pi is another full revolution. 5 pi is another half revolution. So there's 5 pi, or 2.5 revolutions, because each 2 pi is 1 revolution. That's also going to be -1. Yeah. So I would say let's go back and look at a couple more examples because I feel like those are not sufficient. So this is where that blank page is, and you should definitely use the blank pages in there. So what if I wanted to find, say, the 6 trig functions of 3 pi over 2? Well, I'm going to find where that is on the unit circle. So 3 pi over 2 is at the top, bottom, left, or right? Let's see, that angle is 0. That's pi over 2. Pi. That's 3 pi over 2. So what's the point there on the unit circle? Right, the x coordinate's 0, the y coordinate's -1. So then I can find cosine of the angle. I should really write 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2, which usually we find sine first, but I didn't, so I'm going to write sine up here. Sine of 3 pi over 2 is -1. And what's cosine going to be? Or sorry, what's tangent going to be? It's a good question. Tangent is the the y over the x. But what's y over x? Right, which is, in this case, -1 divided by 0? That's undefined. Tangent of 3 pi over 2 is undefined. That's the answer.
Okay, sorry.
No, go ahead.
No question. I'm more like confused than anything.
Okay.
How?
Which part?
Because like, shouldn't it have a value?
It doesn't. So think about it this way. We've talked about the domains of functions before, right? And one of the domain issues a function can have is possible division by 0. And that's the exact domain issue we're running into here.
Okay.
We'll see this more when we actually graph the tangent function, that there are places where it is undefined and has vertical asymptotes.
Okay.
The same thing happens for tangent at 90 degrees too.
That is excellent observation. Yeah, tangent of 90 degrees or pi over 2 radians will also be undefined. In fact, tangent at any of the top or bottom marks on the unit circle or points on the unit circle will always be undefined. Let's talk about the reciprocal functions. What should cosecant of 3 pi over 2 equal? 1 over, right, because cosecant is the reciprocal of sine, 1 over -1, which is -1. All right, what's secant of 3 pi over 2 going to be? Well, not quite. 1 over 0, which is undefined. It's all right. So whenever we divide by 0, it's undefined. And then cotangent of 3 pi over 2. Well, cotangent of 3 pi over 2 is x over y, not y over x. And x over y is 0 over -1. And 0 divided by something that isn't 0 is just 0, because -1 goes into 0 times. So that's how we could evaluate the 6 trig functions of a quadrantal angle. And now here's something that is worth noting. Whenever you have a quadrantal angle, you're always going to get 2 of each thing. You're going to get 2 of them being 0. You're going to get 2 of them being undefined. And you're going to get 2 of them being +1 or -1. So one more example. Let's do the 6 trig functions of theta equal to 2 pi, which is 1 full revolution, which leaves us at the point 1, 0. So there, sine of theta is the y coordinate, which is 0. Cosine of theta is the x coordinate, which is 1. And tangent of theta is what?
0 over 1.
Thank you, which is 0. All right, and then cosecant of theta is going to be 1 over 0, which is undefined. I usually don't like to write equals undefined, but it's not terrible. I would write is undefined. And secant of theta is the reciprocal of cosine, which is going to be 1 over 1, which is 1. And cotangent of theta is going to be what? Which is undefined. And look, again, we see the same pattern. 2 of them are 0, 2 of them are positive or -1, and 2 of them are undefined. It's always going to be true when you find the 6 trig functions of any quadrantal angle. But the way you really do find them, at least the way I find them, is by really just using the unit circle and finding the point on the unit circle and then saying, oh, sine is y, cosine is x, tangent is y over x, and then the reciprocals. And then if you wanted to, you could also use the unit circle to find tangent of 17 pi over 6. I wouldn't. Oh, yeah.
Yeah, the A, B, and C that we just did, can't you, since it's like a couple, either like 1 full revolution or like a half revolution or something like that, can't you just subtract 2 pi until you get an angle that you rectify?
You can also do that. That is true. So we can in fact do that here. For 17 pi over 6, we could say, well, that's going to be the same as tangent of 17 pi over 6 minus 2 pi is minus 12 pi over 6, which is tangent of 5 pi over 6. And I've run out of room.
With radians, you would subtract the pi.
With degrees, you'd subtract 360 degrees. So someone said, like, what's, cosine of 500 degrees, which is not a great angle, but you could subtract 160, and then you'd be asking cosine of 140 degrees.
So why are we subtracting both sides?
So here's the thing. No, you guys are asking really good questions. So if my angle takes me more than 1 full revolution around the circle, let's say let's say I did 1 full revolution and ended up here. If I subtract 1 full revolution, I'm still at the same point on the unit circle, which means the trig functions are going to have the same values. So we often think about angles being the same. The actual language there is coterminal, meaning they end in the same spot. And angles that are coterminal or differ by a full revolution are going to have the same trig values. So whether your angle is, say, let's say, I don't know, whether it's 510 degrees or 150 degrees, right? Here's 150 degrees, or 5 pi over 6, and here's 510 degrees, which is 5 pi over 6 plus 12 pi over 6, which is 17 pi over 6. So that's why we're subtracting it, because it doesn't matter how many revolutions you do in the unit circle, the spot you're at is what determines what your trig function values are. Yeah, come on. So when we subtract 12 pi over 6, right, we're still in the same spot in the unit circle. And then tangent of 5 pi over 6, I know is going to be negative because we're in quadrant 2. And I know that the value is going to be, I'm thinking of the unit circle, to be honest, or not the unit circle, the special triangle. I'm thinking my special triangle angle is pi over 6. That's the reference angle, and the opposite's 1, the hypotenuse is 2, the adjacent is √3. The tangent's going to be opposite over adjacent, which is negative 1 over √3, which, yeah, we should rationalize is negative √3 over 3. So that's how I would do that problem. Yeah, Jake.
Could you not have just found the reference angle as pi over 6 because you're given the same point of value? And so
Totally,
pi
yeah.
over
You can
6.
totally say, right, 17 pi over 6 definitely has a reference angle, pi over 6.
And then you just
But then you still have to know what quadrant you end up in to know if it's positive or negative.
okay.
Right? No, you're thinking the right thing. We just have to be like, we still have to know what quadrant we end up in.
Okay.
I still don't know where 12 pi over 6 is.
So what we did there was we said that basically, if you go back to the unit circle, it's all right. So if we go back to the unit circle, 17 pi over 6 is 2 pi. I'm sorry, you can't see. 1 full revolution is 2 pi, which is 12 pi over 6. And then another 5 pi over 6 gets me here. So that angle is 17 pi over 6, which is 1 full revolution plus another 5 pi over 6. And what I'm trying to do is get an angle that I recognize better. So I'm saying, well, 17 pi over 6 ends in the same spot as 5 pi over 6 if I just subtract off a 2 pi. I'm subtracting the 2 pi to see that the angles end in the same spot. Another example of this would be, I'm always running out of room here. Let's say we wanted to find sine of 8 pi over 3. Well, 8 pi over 3 is going to be 1/4 evolution, which is how much? 2 pi, which is how much pi over 3? I'm multiplying 2 pi by 3 over 3 to get 6 pi over 3 to help me see how much more I need to go. I've gone 6 pi.
1, right? That's where the 3.
Yeah, I'm multiplying by 1.
Okay, gotcha. Sorry.
Yeah. And then I'm still going to go another, I need 8 pi over 3, so I'm going to go another 2 pi over 3. So that angle is 8 pi over 3. But it's essentially the same as, or is coterminal with 2 pi over 3. Because if we go back 1/4 evolution from there, if we subtract 2 pi, that's going to be 8 pi over 3 minus 6 pi over 3, which is 2 pi over 3. So these angles, 8 pi over 3 and 2 pi over 3, end at the same spot. So if I'm trying to find sine of 8 pi over 3, it's the same as finding sine of 2 pi over 3. Oh, question, yeah, sorry.
Okay, so I know where 6 pi over 3 came from, but how did you know how far to make that jump to get to 8 pi over 3?
Well, because once I got 6 pi over 3, I knew I had how much left to go. 2 pi over 3, because I know I need to go from 6 pi over 3 to 8 pi over 3. So I need a difference of 2 pi over 3, and I know from the unit circle
Oh,
that 2 pi over 3 ends right over there in the second quadrant.
Sorry.
No, you guys are asking very good questions. Like, don't be sorry. These are I think we're developing a better understanding of what's going on here from all your questions. So please,
So you can also just subtract 2 pi.
you can also do that, yeah. And then the angle would be, well, sine of 2 pi over 3. I know the sine of pi over 3 is 3 over 2. So sine of 2 pi over 3 in the second quadrant is positive root 3 over 2. Okay. So a couple tree identities. One we've already mentioned is that tangent of theta equals sine theta over cosine theta. And I will also point out, even though we've already said it, that cotangent theta equals cosine theta over sine theta. The other tree identity, and this one comes up a lot, I usually call it the most famous tree identity, is that sine squared theta plus cosine squared theta equals 1. And if you want to think about why that would be true, let's go back to the unit circle for a second. So this point here, which is cosine theta, sine theta, well, that's the x and y coordinates of a right triangle with a hypotenuse of 1. And if I say, well, okay, well, that's my cosine theta side, which is x, and my sine theta side, which is y. If we use the Pythagorean theorem, x squared plus y squared better equal 1 squared. But x is cosine theta. And y is sine theta. So cosine squared theta plus sine squared theta should equal 1. And this is called a Pythagorean tree identity because it's literally coming from the Pythagorean theorem. We're not going to finish this up today. The last thing I want to show you, though, is that this tree identity is true for any angle you put in. So if I actually put in 4 pi over 3, sine squared of 4 pi over 3, sorry, thank you, I'm way zoomed in. Yeah, good call. Plus cosine squared of 4 pi over 3. That's going to be sine of 4 pi over 3 quantity squared. This is just a shorthand notation for that. We just don't like writing this every time. That's going to be cosine of 4 pi over 3 squared. And that's going to equal, well, sine of 4 pi over 3 is, let's see, 4 pi over 3 is in quadrant 3. Sine of pi over 3 is root 3 over 2. So sine of 4 pi over 3 is negative root 3 over 2. Cosine of 4 pi over 3, well, again, we're in quadrant 3. Cosine of pi over 3 is 1/2. Cosine of 4 pi over 3 is negative 1/2. And then a negative thing squared ends up being positive. So we're going to get positive 3 over 4 plus positive 1 over 4, which is 4 over 4, which is 1. Works out. And that should be true for any angle you put in there. All right.